Now we want to generalize some of these ideas that we've kind of started at with the Nernst equation by talking about cells and equilibrium. So what would it mean for a cell potential to be 0 volts, right? E cell is equal to 0 volts. That would tell us that there's no driving force for electrons to transfer from the anode to the cathode. Well, what is the driving force that normally pushes electrons? Chemistry, right? The chemical reaction normally is occurring. Reactants are becoming products. So a cell with a potential of 0 has no net chemical reaction happening. There is no transfer of electrons from the oxidation process into the reduction process. Instead, there's just nothing happening. There's no flow of there's no chemistry that's happening. So therefore, your electrons aren't flowing between the anode and the cathode. So if a cell has a potential of 0, that means the underlying reaction is at equilibrium. There's no net transfer of electrons. So you have a cell potential of 0. That would also mean your reaction quotient, your actual mixture of reactants and products, is equal to the equilibrium constant. Okay, so that you're just kind of going through that. You're at equilibrium. There's no more kind of net flow of electrons. Your reactants aren't changing to become the products anymore. It just is stopped. So if we take these two statements, we can basically take our Nernst equation and do some substitutions. We can say the cell potential is 0 and that the reaction quotient is our equilibrium constant. So we can plug those in. We can then do basically some rearrangement. And we can see there is a direct relationship between the cell potential and the standard cell potential and the reaction equilibrium constant. And so what that tells us is that these two things, which we've seen, are kind of implying the same thing of how much do your reactants want to become your products versus, what you're at right now, what is the current status. And so we can see that these two values are going to be directly related to each other and describe kind of the tendency of your reactants to become products. So let's take a look at the equation we've seen in previous examples. Zinc plus the copper 2 cations. I want to know what the equilibrium constant for this reaction is at 298 K.
All right, so what is the equilibrium constant for this reaction at 298 K? So we know equilibrium constants are very useful for describing chemical reactions. How much is, reactants product present under your equilibrium conditions? What does the, reaction do? So we want to come up with some ways to calculate that. We've seen some before previously. But one of the things we want to note about this reaction in particular is that it is a redox reaction. We can see that we have a element becoming an ion. That means we have to be moving around electrons, ion becoming element. So that implies that there is definitely a flow of electrons, some electrons moving around here. And so what we want to do, or if that's true, then we can always relate that to use the equation that E cell naught is equal to RT over NF ln of K equilibrium. And so even though this reaction may not be happening in a cell, we could do this reaction in just like a beaker or anything we wanted. We don't have to necessarily run it as a cell, but because we could run it as separated half reactions, we can figure out what the cell potential would be for that reaction, the standard cell potential from just tabulated data, and then relate that to the equilibrium constant. So how this equation is written, it's easier to plug in a value for the equilibrium constant and then get that into the cell potential. Instead, we want the equilibrium constant, so we're going to need to do some algebra and rearrange this equation. So I want to isolate the equilibrium constant, which means I need to get rid of this fraction. So if I want to functionally divide by this fraction, which is the same thing as multiplying by the reciprocal. So what we end up with, the other side of the equation will be NF E cell naught divided by RT. So basically the reciprocal of this fraction multiplied by E cell is equal to ln of the equilibrium constant. And so if I want to isolate out the equilibrium constant, I need to get rid of this natural logarithm. So do the anti-log, which would be the same thing as raising this as an exponent of e. E to the NFE cell naught over RT is going to be equal to the equilibrium constant. So these two equations describe the exact same relationship. The cell potential, standard cell potential, related to the equilibrium constant. And which one you use is just going to be kind of based around, if you're given the equilibrium constant, then you use this equation, plug it in to get the cell potential. If you have the cell potential, you can plug it into this thing to get the equilibrium constant. So here, because we know our chemistry, we can figure out all this cell potential and all that kind of stuff. So we've seen this reaction so far in the Nernst equation analysis. So Zn solid oxidizes to Zn2 plus the 2 electrons, copper 2 plus the 2 electrons becomes the copper solid. So one of the things we can see from this is that I have the 2 and the 2, so N is equal to 2. And we could use our tabulated reduction potentials and see that the cell potential is 1.10 volts. So we've seen that previously in the other examples, looking at the Nernst equation, what the cell potential was. So we can take that, plug all of those in. N is 2. F is a constant, 9.65 times 10 to the 4th coulombs per mole, times the cell potential is 1.10 volts. R, constant, 8.314 joules per mole Kelvin, times the temperature is 298 Kelvin. So R and F are always going to be constants, so you can always plug those in. Cell potential and the N depend on the chemistry, and then the cell conditions we do want to be mindful of. You can normally assume it is 298 K, but not always. 8.314 divided by 298. And so what I get from that is, if I evaluate that, I would get that the equilibrium constant equal to E to the 85.7. Oh, so one of the things to note is if we look at these units, the per moles cancel out, the Kelvin and the per Kelvin cancel out. So then I have C times V divided by J. And so it ends up that coulombs times volts is just equal to joules. And so if I divide both sides by joules, I just get 1. So we can see that these combine, coulombs times volts cancels out the joules. So we end up with a unitless value. Whenever you're taking an exponential, you always want the top to be unitless. So that's good. So if I actually take e to the 85.7 power, I get that the equilibrium constant is 1.6 times 10 to the 37. So pretty big. That's a very, very big number. This is common for equilibrium constants for these electrochemistry reactions. That's why we use electrochemistry reactions to drive batteries, to drive power, to drive the flow of electrons in useful kind of situations, because they are very, very product favored. You are going to be able to really react all of these reactants. That also kind of tells us why when you reacted like 90% or 99%, the cell potential doesn't change that much in the Nernst equation, because you are still nowhere close to equilibrium. Equilibrium, it's the 10 to the 37th power. We were at like 190, 199. That's not that big of a Q. You're nowhere close to equilibrium yet. You need to do a lot of reaction. There's a lot of push for forming products, which is consistent with having a positive cell potential. So positive cell potential and a K that's greater than 1, in this case, a lot greater than 1.
So this relationship that we've seen, we can relate the cell potential and the equilibrium constant, and this combines with previous relationships we've seen between the cell potential and delta G, over here, and our delta G and our equilibrium constant. And so we have those relationships kind of all linked together, and we have now, there's these equations that kind of all fit together, describe these relationships, but all three of these values impart the same information. They all give you information on the direction of a reaction. Now it's important to note delta G naught and the equilibrium constant K apply to any type of reaction, whereas E cell only does apply to redox chemistry. So it only applies to redox chemistry, but it applies to any type of redox chemistry, even if you're not actually doing it as a cell, if you haven't separated your reactants into the different cells, it still does describe kind of the tendency of the reaction to occur. And they all, in terms of if you want to know spontaneous in the forward direction, these three values all impart the same information, different relative kind of values. So delta G is negative, right? Negative tells you it's spontaneous, delta G negative, E cell positive, and K greater than 1. So there are three different kind of descriptions, but we can look at them and kind of understand and predict how your reaction mixture will change in order to reach an equilibrium. And so they all kind of give the same information. You'll note these three kind of things we're looking at. Other things like delta H and delta S of the reaction don't, kind of are part of the delta G, but they're not explicitly telling you whether or not the reaction is spontaneous. Participation 410, question 1. What is the equilibrium constant at 298 K for the following reaction if E cell naught equals 1.54 volts? 3Ag plus and Cr become 3Ag and Cr3 plus. This is the first question on participation 410, due Friday, April 10th, over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, what is the equilibrium constant at 298 Kelvin for the following reaction if E cell naught is 1.54 volts? Silver ions react with chromium to make silver and chromium-3 ions. All right, so we've got a lot now for these cell kind of potentials. For cells, right? If you have your two half reactions, you can predict which one will preferentially reduce, which one's going to oxidize using your standard reduction potentials. You can design cells, build cells, predict standard cell potentials, balance the redox reaction, use the Nernst equation to see how that potential will change over time. This is only for standard conditions. What about the conditions of the cell you're actually using your cell? You're taking that transfer of electrons out of it. And then we can also do things like determine delta G naught and determine the equilibrium constant for the reaction. Those are two really useful things. Delta G gives you information about spontaneity, but also gives you information about how much energy you can get out of a reaction. Equilibrium constants are necessary for predicting relative amounts at equilibrium. Those are really important considerations. And one of the things is they're relatively difficult to measure. Standard cell potentials and cell potentials are relatively easy to measure. You just use a voltmeter, and so that is much easier to measure. And then you can take those potentially easy to measure values and turn them into interesting but hard to measure values like the delta G and the equilibrium constant. So we got a nice kind of comprehensive use and kind of description of these spontaneous chemical cells, electrochemical cells. All right, first video down, and we already got a participation question. It's gonna be due Friday. I got the homework due Saturday. Marker will take self pulse lab due Sunday, and don't forget the lab technique presentation questionnaire over on Blackboard. You want to get that filled out by Friday evening. If you have any questions or anything, let me know. Otherwise, welcome to this final set of videos for week 12 and for chapter 17. See you in the next one.